Okay, let's take a look at how to balance chemical or nuclear reactions when the element emits a beta particle. Something that is very important that you need to remember is how to write the notations for alpha particle, which we just did, beta particle. Note that the mass number for beta particle is 0, but I have a -1 down here by the z, whereas for alpha I had a 4 and a 2. Therefore, it's going to change a little bit, the equation is. But the principle remains the same, that whatever I have on both sides have to equal. Beta radiation is the only radiation in which the z number increases instead of decreasing, because I have this -1 here. So let's take a look and see how we can balance this out. I have 20 on this side, so we can write it once again as a chemical or a mathematical equation. 20. Now I run into this arrow, which means it's my equal sign, -1 plus x. So if I write it as x minus 1, right, it's the same, -1 plus x, x minus 1. And so if I solve for x, I have to move the -1 across the equal, so it would be 20 plus 1, which means 21. That means that my z will be 21. Once again, the beta decay increases the z number by 1. It's the only radiation that does that. Therefore, instead of calcium 20, I get 21, which is Sc scandium. Okay. Now note that beta has a mass number of 0, which means that the top number is not going to change, because 0 plus x has to equal 45, which means that this has to be 45. 0 plus 45 gives me 45. So I'm balanced up on top. 21 minus 1 gives me a 20, so I'm balanced at the bottom too. Now let's take a look at a slightly different example. Now here you know that this is going to be beta radiation, but in a quiz or in a test, you may not have a clue because it may not tell you. But if you're given the original element and then what it decays to, you should be able to figure out by which particle it's decaying. So as you see here, I have x. I don't know the z, but I know that 6 has to equal 7 plus x. So if I solve for x, it will be 6 minus 7, which is -1, which means that my particle will have a -1 z down at the bottom. And the only one that does that is a beta particle. So I know how to write it as beta. Now because my top number doesn't change, that means the mass number for beta is 0. And there you have it. Now let's do a slightly different example where we have to calculate the original element. 54 minus 51 equals 53. So my element 53 is iodine, if I look it up in the periodic table. 131 plus a 0 is 131. Therefore, this is my mystery element or original element that decays into xenon. If you want to double check, I have 53 on this side. -1 plus 54, or 54 minus 1 is 53. Therefore, I've done it correctly. Now let's look at the next two examples. Here I have to figure out what it decays to, and here I have to figure out the original element. 11 has to equal x minus 1, which ends up being x is equal to 11 plus 1, which makes it a 12. And element 12 is magnesium. And then the top number is going to still be 24 because this is a 0. So 24 equals 0 plus x. X is 24. Okay, and then the last problem that I have here, I have to figure out the original element, which means 20. I can do it -1 plus a 20, or 20 minus 1 is 19. So if I look that up, it's going to be potassium. And then 42 plus a 0 is 42. It doesn't change. Therefore, this is going to be potassium 42. Remember, as I said, that the beta decay will always increase the Z number of the original element that decayed by 1 to the next, to produce the next nucleus in the periodic table. So potassium and calcium are right next to each other, and calcium is the one, it's to the right as you look at the periodic table, is to the right of potassium. This is how you work the nuclear reactions with a beta decay. I'm going to erase this, and then in the next slide we're going to work on balancing nuclear reactions with a positron emission.